Well, welcome, folks. It is our brand new unit, Chemistry, Unit 5, Stoichiometry. Hey, Mr. Sams, can you say stoichiometry?
Not this early in the morning.
It ain't early in the morning. It's only
6:30.
6:40.
6:30 when we got here.
Yeah, well. So,
It's still dark outside.
not really. It's just a little light.
Ugh.
Come on. Can you say stoichiometry? No. Okay. Everybody say stoichiometry. Stoichiometry. I want to hear you. Stoichiometry?
Stoichiometry.
He said it. I knew I could get him to say it.
I'll get more into it once I get closer to the bottom of that cup of
You
coffee.
need that coffee. Hey, yeah. I had yogurt this morning.
I have a muffin too.
There you go. Chocolate muffins. There you go. Actually, I did stop and get something to eat. I haven't eaten yet. Okay, hey, podcast 5.1. Cinco y uno, right? In Spanish, I think, right?
Oh.
Okay. All right, we're going to talk about the introduction to stoichiometry. Sometimes abbreviate stoichiometry as stoic. Think of that, stoichiometry. Kind of works for me, yeah. Talk about multiple calculations and mass calculations. Let's go ahead and do that. Hey, what is stoichiometry?
Some tells me it's predicting the quantities in a chemical reaction.
Hey, where did you get that from?
I don't know.
You're
Years of
amazing.
experience.
Yeah. Hey, what do you mean by predicting quantities in a chemical reaction?
Predicting quantities, that can show up in a number of ways, either the number of moles of something, or the number of grams of something, or liters of a gas, or milliliters of a solution, things like that.
So if you have a reaction that says A plus B plus C or something, or make C or whatever, which would be what type of reaction, by the way?
That would be a synthesis or combination reaction.
You're good. You're really good. Hey, and let's say that you knew that you had 5 grams of A.
Mm-hmm.
What would stoichiometry be able to help you figure out?
Well, it could tell us a couple things. It could tell us how many grams of B would react with that. It could also tell us how many grams of C we could produce.
How much B or
How much C.
how much C?
Yeah, and that could be in grams, or like I said earlier, we could do moles, or if it's a gas, liters, or
Yeah, that
all
works
sorts
for
of
me.
things.
Yeah, pretty cool. Okay. Hey, I think we should do a little video clip that helps us understand this whole concept of predicting products.
Okay.
Let's do that. Okay. Well, here I am with my bicycle. This is actually my racing bicycle.
That's a bike?
It's a bike.
Holy cow.
Well, it's kind of a bike. It's kind of got some problems. I think it's not complete. I don't think I could ride that in a race, Mr. Sam.
No, well, you could. You'd probably come in last.
Yeah, because I think I'd have an issue. Ouch. Ouch. There's no seat.
Yeah, you might want that. That could be a little uncomfortable for after 100 miles or so.
I'm missing something else.
Well, you
I'm
do need
missing
wheels to make
wheels.
it go.
Yeah, there's no wheels. Hey, look what I found.
Hey, look, a seat.
A seat.
What are the odds?
I don't know. It's amazing. We found the seat.
That doesn't look much like a seat either.
I know. It's kind of a funny looking seat. It's designed for speed. So, hey, let's talk about mole-to-mole ratio.
You know, it looks like a salmon steak.
Well, it's a seat.
It does.
Okay, so this is a seat. Yeah, it's a kind of a racing seat. We want to talk about mole-to-mole ratios. You see, to build a complete bike, we need to have a recipe to build the complete bike. Well, to build the bike, you need the frame. Those are the parts, too, but they're already connected. And I think it's important that we have one seat. Wouldn't be good to have 2 seats. It'd be a waste of weight. So I put the seat into the staff right here. Of course, I tighten it all up so that it doesn't slip, and that would be a problem, right? Okay. So seat's all tight, right? What else do I need, Mr. Sams? I'm missing something.
Yeah, you're kind of missing the wheel part.
Oh, wheels! Okay, well, I've got one wheel. Okay, good. So we're good. So let me put the wheel on.
Okay.
Okay, so we're going to be good. All right, I got to put the wheel on.
All right.
Okay.
Now, are you good at riding wheelies?
Huh?
Are you good at riding wheelies?
I'm good at everything, Mr. Sams.
Oh, really?
Yeah.
So I'd like to see you ride a wheelie around this room on your one-wheeled bike.
My one-wheel bike.
Yeah. You're
So
putting
I
one
need
wheel.
more than one wheel?
Well, you know, it is called a bicycle
Why is it called a bicycle?
because there are 2 wheels.
Yeah, these are proper. See, this is the new bike. A different kind of a system for its wheels. Ah! It also would be good. This is actually good practice. This is my new bike, and since it's kind of new, I've never had a flat with this. So it's hard to get off this morning, and now it's hard to get back on. Mr. Bergman, his old bike, could have done this in like 5 seconds. Ha! There we go. It's a back entry. It's very easy for faster. Ha! There we go. So I got my bike. I'm ready to go.
All right.
On the wheel. Okay, got the seat. Hold
All right,
too tight.
ride that wheelie.
All right, okay. I got a problem.
You do.
I think I need
2.
two. Buy. Oh, buy. So
Bicycle.
buy means two. Oh, what? Hey! What are
Hey,
you
look,
doing?
another wheel.
Another wheel.
What are the odds?
I don't know. So I can hook this up. I think we might be able to make it work. So what's the recipe to make a bicycle, Mr. Sanders?
Looks like you need a frame,
Frame, good.
1 seat,
One seat.
and 2 wheels.
Yeah, it's not going to work without having both wheels.
Okay. Unless you're really good at riding a wheelie.
Unless you're good at riding really, and for a long distance triathlon, that would be a long day. And a seat would be kind of important because if you don't have a seat,
That's going to hurt.
it's going to hurt a
Yeah.
lot. Yeah. So the recipe is 1 frame plus 1 seat plus 2 wheels makes
A bike.
1 bicycle. Well, Mr. Sams,
Yeah.
I was having a hard time building my bike there.
Yeah. How long did it take you to get that back wheel on?
I don't know. Maybe longer
while.
than I should have taken. But yeah, hey, what's the recipe?
1 frame.
1 frame. We'll call it an F.
Okay.
Kind of like for chemical symbol.
All right.
Yeah.
1 seat,
Plus 1 S
and then 2 wheels.
plus 2 W makes
1 bike.
1 BK. Hey, like BK bike. That works, right?
All right.
So there's our relation.
Mole ratios. Ratios.
Yeah, we have ratios.
Yeah.
So you can actually write these as ratios. What we're trying to get to, guys, is we're trying to introduce a new concept. Is that, we've learned about mole conversions, and you've learned that 1 mole is equal to 22.4 liters. Mm-hmm. You've also learned that 1 mole, I'm writing as a fraction, Mike. I can, anyways, is equal to what else?
6.02 times 10 to the 23rd.
6.02 times 10 to 23rd particles. Mm-hmm. And 1 mole is equal to
The molar mass in grams.
so many grams of the chemical.
Right.
But those are our 3 fractions, right? But what we're going to introduce today is 1 more fraction.
Yeah.
It is the mole to mole fraction.
Yeah, and then, guys, this one's really easy because it all comes from the balanced chemical equation. However, in order to do it, you have to have
A
a
balanced-
balanced chemical equation.
So, guys, this is what we have. We have a balanced chemical equation here, our balanced bicycle equation.
Right.
And so we can say 2 moles of wheels is equal to
1 mole of bike.
mole of bike. Or we could say 1 mole of seat is equal to 1 mole
of frame.
of frame.
Now
And these
notice-
can be flipped around if you know.
Yeah, we can flip them upside down, and you can do a ratio from any substance to any other substance in a balanced equation.
So
It
wheels
does-
to bikes,
Yeah.
seats to wheels, wheels to seats,
Yeah.
seats to frames, frames to seats, frames to bikes, bikes to frames,
Yeah,
whatever it is.
Whatever. It doesn't matter. It does not have to be products to reactants or reactants to products. It can be 2 reactants. It can be 2 products.
That's right. So let's
anything.
do this. Now we've done a sort of our analogy with the
Yeah.
bike, but let's do it with like real chemicals.
Okay.
Okay, so let's do that. Yeah, that's not that important. Okay, this is important. Why is this important?
Because in a chemical reaction, things react in a specific proportion.
Yeah.
Yeah.
All right, so let's use an example here. So here's a real chemical equation. We have 3 hydrogens get together with 1 nitrogen to make 2 ammonia. So
Yeah.
we can build mole-to-mole ratios here.
Now, one thing about the balanced equation, folks, is the numbers in front, the coefficients. Those refer to specific numbers of molecules on a really small scale. They also refer to number of moles
That's
on a
correct.
larger scale.
Exactly.
So either way, we can use them as that ratio.
So let's build some mole-to-mole ratios. I
Okay.
can say now 2 moles of NH3 is equal to 3 moles of H2. Now, folks, here's something very important. Remember, we've talked about the naked numbers. You must not just write 2 over 3. In fact, you can't just say 2 moles over 3 moles.
No.
You have to say 2 moles of NH3 over 2 moles of hydrogen. You
Yes.
must have the number. You must have the unit, moles. You must have the chemical, hydrogen, or ammonia, or whatever it might be. So this is 1 fraction. Can we think of any more here?
Yeah, sure.
About
Let's
6 of them, I
yeah,
think.
there are 6. Let's do 1 mole of nitrogen.
Where'd you get 1 mole?
I
I don't see a 1 anywhere.
Well, if it's blank, it's a 1.
Yeah, so right here, folks, we've got N2, but there's no number, but of course that implies it's a 1. 1 mole of nitrogen is?
Over 2 moles NH3.
Okay, and we could flip this, guys, right? We could also write 2 moles of NH3 is equal to
1 mole of N2.
1 mole of N2.
Well, why don't we go ahead and flip the first one we did, the 2
Oh, yeah. And we could flip this one, and we can say 3 moles of hydrogen is equal to 2 moles of NH3. We need these numbers, guys, if we're trying to predict, how many bicycles we're going to make. So if I had 16 wheels, I could predict how many bicycles I could make. Okay, and then I could figure it out pretty easily. All right. Actually, should we do that?
What?
So if we go back to our bicycle recipe, let's say we had 16 wheels.
Right.
How many bikes could I make?
I don't know, but I think if I had a ratio that I could figure that out.
So what you do is you'd say 16 wheels.
Start with what you know and put it over 1. Okay.
Times a fraction, or
Do the railroad track thing.
Railroad track thing. Well, I know that in my recipe there are 2 wheels. So I'll say 2W.
And I want to know how many bikes we're going to make.
Well, the ratio is 2 to 1. So I can say
1 bike.
What happens to W?
W's cancel.
So it's 16 times 1 over 2. Well, that's just
8 bikes.
8 bikes. Now, guys, you knew that. Of course, if you had
Right.
16 wheels, you can make 8 bikes. But we need to show it to you sort of dimensionally, mathematically,
Now,
because that's how you're going to do this
Right.
in the...
That's why we taught you railroad tracks in Unit 1, so you could do it here.
yeah.
Now, there's one assumption we're making here, Mr. Bergman.
What's that?
Well, we're assuming that we have
Plenty.
of frames and seats.
Yeah, and later on we'll talk about what happens when you don't have plenty of frames and seats. So.
But for now, assume that if there are more than one reactant, that you have plenty of the other one, and that you're only limited by the one that you have.
Good. All right, now let's go back forward. All right, so now that we have kind of figured out the whole ratio thing, Mr. Sams, I think we need to discuss what was called the mole map. So it helps us to understand how to do these calculations.
And guys, if you look in your packet, the mole map is in your packet. It's page 3 or 4 or something like that.
Right, and if you're watching this on the internet, as some of you I know are, you're gonna, your teacher, whoever bought the CD or the DVD, can get access to that on the DVD. So, okay. All right, so this is called the stoichiometry flowchart, or sometimes we like just
The land of the mole.
I like the mole map. It's a little simpler.
But you don't get to say it like the land of the mole.
You say the mole map. No? Okay. No. All right.
All right, guys. Notice there's a few things X'd out. We're not going to talk about those in this unit. Those are on units to come. So that you'll actually be using this probably pretty much for the rest of the year. So hang on to it. Don't lose it.
Yep.
All right.
So we've got representative particles.
Particles, yeah. That's like atoms and molecules.
Atoms and molecules.
Yep.
Now we've actually kind of done, if you will, if you think about this, kind of divide
we've
this
done
in
half.
We've done the first half already in the previous unit, or 2 units ago, I guess, when we converted grams to moles and moles to whatever. So if you want to go from representative particles to Avogadro's number, then you get moles. And that moles to molar mass, or to grams, you'll use the molar mass right here. These are the conversion
Those are the
factors.
conversions there on the arrows.
And then if you're going to go to liters, you use the 22.4 liters.
Yeah.
And there's some other things that we'll worry about later. But there's something very important here called the mole ratio.
That's how you go from one substance in the reaction to another substance in the reaction.
So we have a given chemical, moles of A, and we're trying to find a new chemical, chemical B.
Yeah.
All right? And so we'll use this as we do a couple problems,
Yeah.
and that'll be more obvious. Okay. So when we're doing a mass calculation, here are the rules that you need to follow. Number 1, balance the chemical equation. Number 2, write down the amounts under each chemical. Number 3, put a question mark and a unit by the chemical in question, and then do the stoic to determine the amount. So these are the rules. So I would recommend you just pause the video and copy this down.
Okay.
Okay. All right, so let's do an example.
Let's do one.
12.3 moles of potassium chloride. Now, what was rule number 1?
I believe it said we had to have a balanced chemical equation.
Hey,
Look, we have a balanced chemical equation.
Mr. Sams, you wrote a balanced chemical equation. That's pretty good. All right, so we
pretty
got
nice
a
of
balanced
me.
chemical equation. It was given to you. Sometimes you're not going to have a balanced chemical equation. You're going to have to figure it out what it is.
Just like you did in Unit 4.
Like Unit 4. So, okay. So now what we do is we write down what we know underneath what we know.
Okay.
So we have potassium chloride, KClO3, and I know I've got 12.3 moles of it. So I write it underneath there. So
And guys, this is just kind of the planning stage here. We're not solving the problem yet. We're figuring out what we know and where we're headed.
And then it says how many mole of O2 will be formed. So O2 is right here. So I'm going to put a question mark. See how I'm following my rules under there, and I just put a question mark and I'm going to write what unit I want in it. I want moles. So I want to convert moles of this to moles of that. Basically, if I've got 12.3 moles of potassium chlorate, how many moles of oxygen will I produce? How many bikes will I make, if you will, in our analogy?
Yeah, so let's go to the mole map here real quick, or to the land of the mole.
That's painful, Mr. Sanders.
I know.
All right, so right now we have moles of a chemical. We had 12.3 or whatever, right? And then it asked us to go to moles of B. Well, just a mole to mole.
Yeah.
So in this mole map, all we need to look at is this portion of the box.
On this problem, yes, because we have moles, we're going to moles, so our step is we just use the mole ratio
right here,
to
it's
get
very
there.
important that what we're going to be doing is doing the mole ratio. So I start with what I know, which
Put it
is
over 1, 12.3 moles.
12.3 moles.
Of KClO3.
Of KClO3.
Not just moles.
Yeah, over 1.
Okay. Now the mole ratio, where do we get those again?
Well, that's from the balanced chemical equation. So there's a 2 here. And so I'm going to say, well, actually, you know what I like to do? I say moles of KClO3, and I want to go to
Moles of O2.
moles of O2. I like to just put the units first and then go add the numbers later. And so if I look here, what number goes here? This number is a 2. And up here for oxygen, this is a 3. So now I get my calculator out. So Mr. Sams is furiously typing on the calculator. So 12.3 divided by times 3 divided by 2, and you get what?
18.45.
18.5 moles of oxygen. The moles of KClO3 here
Those units cancel.
and you're left with moles of oxygen. That's it. So if you start with 12.3 moles of this, you will make this many moles of oxygen, 18.5. It's just figuring out how much you're going to make, or how much it came from, or whatever. Okay, well, let's do a different problem. In this case, let's do a gram to mole problem. So you need to start with the balanced equation.
Hey, look, we have a balanced equation.
It's actually the same equation. So we're just trying to kind of make sure you understand it. So, guys, something very important that you ought to do is to write down these examples. As I've been checking some students' notes, they're not writing all the examples, and these examples are critical to help you understand this. So what are you going to do? Write the examples. If you don't, Mr. Sams will take your thumb. Oh, no, he won't.
No, I won't do that.
Okay, never mind. 4.53 grams is what I know of potassium chlorate, so I know that. Okay. How many moles of oxygen? Okay, hey, it's kind of like the same problem.
Yeah, we're just going to have
but
one
we're
additional.
starting with a different unit.
Yeah.
So maybe we should look at the
Mole map.
mole map. Okay. So what have we got, Mr. Sanders?
We have grams of a substance.
So we're up here on the mole map.
Yep, and we're going to moles of another substance.
So I need to get from here to here.
Right. So to do that, we're going to have to go through moles of A.
So it's like a two-stepper there.
It is a two-stepper.
I would call it a three-stepper because you start with what you know. So we have to use the molar mass and we have to use the mole ratio. Okay, so well, let's do that.
Okay.
So well, we start with what we know. It's a fraction over 1, right? So 4.53 grams of KClO3. Okay. And, well, we need to use the molar mass
We
first.
do.
So you'll say grams of KClO3 to 1 mole of KClO3. So we have grams of KClO3.
Yeah.
The number is, now Mr. Sams, I'm going to amaze you because I did
know
not
this off the top of your
use
head?
my
Oh,
calculator.
come on.
I know this number off the top. It's 122.5.
It is.
122.5. Now,
I
where did you get
calculated
that, by the way? Make sure we understand that for our students' purposes.
Apparently out of thin air. No. I just added up the masses of potassium, chlorine, and 3 oxygens. So 39 plus 35.5 plus 3 times 16.
And we got that on the periodic table, guys.
We did.
So just for its molar mass. So
Yep.
so the grams of potassium chlorate cancel.
Okay.
Now we've done the mole to mole ratio. Now what we need to do is we want to
Well,
go
that was
from
grams
our-
to
the
mole.
grams to moles.
Now we need
now
mole
we
to
need to do
mole.
mole to mole. That's what I meant to say. All right. And so now I've got moles of KCl3. So I'll put moles of KCl3. Notice I put the thing on the bottom first because that's what I want to cancel out. And I'm going to say moles of O2. And I get that number. Now, where do I find that number? I don't see that
That
anywhere.
comes from the,
yes.
the balanced equation.
The balanced
2
equation.
and 3.
2 and 3. Now the 2 goes with the KCl3.
Yes, it does.
And the 3 goes with the oxygen. So
Okay.
now this one times on top and divide on the bottom. So 4.53 times times 3 divided by 122.5 divided by 2 equals
0.0555.
and that will be moles
Of
of
O2.
oxygen. All right. Now we're not showing the calculator, guys. I think you guys are good enough with a calculator at this stage of the game. Hey, what if we went from
grams to grams.
So this problem, we're going to go from grams to grams. So let's figure out what we got. We got 8.26 grams of O2.
Wait. We're starting with a different thing this time. We're not starting with grams of KClO3.
Yeah. So
What? We can start with a product?
Yeah.
Guys,
So
you
have
can start with anything. Doesn't matter.
Yeah, 8.26 grams of oxygen and asking for how many grams of potassium chlorate. So this is a gram to gram problem.
Yeah.
So now we should probably look at
probably
the
go to the mole map.
Mole map, okay. So we're starting with grams of A, okay,
And we're going to grams.
of B. So we need to go from here to here, but there's no
We
line.
can't go straight through. We have to go through the land of the mole.
So we use the molar mass,
Yes.
and we get moles. Then we go from moles to moles, and then we go from moles to grams,
Right,
using
so
the
we use
molar mass twice.
molar mass and
Why,
then mole
why should
ratio.
we use the molar mass twice? That
Two
just seems
diff-
like silly.
Two different substances.
That's the key, guys. We have two different substances. They have different molar masses. Okay. Okay. So let's figure this out. Okay, we have 8.26 grams of oxygen. Now notice, by the way, guys, I'm really trying to write everything way over on the left side because I know this is going to be a very wide problem, and so just to kind of keep in mind, this is not like center your text kind of a thing. All right. So then I'm going to say, okay, I want to go from grams. So I'm going to use the first step was the molar mass.
Right, molar mass.
So I'm going to say grams of oxygen to moles of oxygen. 1 mole of oxygen is 32 grams. O is weighs 16, so 16 times 2. It's actually 50.999 or something like that. Okay?
Close enough.
So close enough to 16. Technically, we like to go to the 10th of a decimal, so it would be 32.0.
Yeah.
All right, so grams of oxygen cancel. So now I have moles oxygen. Now I need to get rid of moles oxygen. So I'm going to just put moles of oxygen on the bottom.
Right, so this is the mole ratio step. To go from moles of one thing to moles of another thing, we use a mole ratio.
So then I'm going to say moles of potassium chlorate. Now I get this from the balanced
The balanced equation.
chemical equation.
Yeah.
So this will be a 3, and this will be a 2. Mm-hmm. And the moles of oxygen cancel. I've got one more step because I asked to find grams.
Because now we need to go from moles to grams, so we use the molar
And we've
mass,
done that.
this time of KClO3.
Moles of KClO3 to be grams of KClO3.
And we do that using its molar mass. And Mr. Bergman, you memorized that, I believe?
Yeah, 122.5.
Okay. So I have limited brain space. I try not to memorize things like that.
All right, so Mr. Sims, if there's numbers on top,
Yep.
what do you do?
We multiply it.
In the bottom?
We divide.
So it'll be 8.26
Yep.
times 2 times 122.5 divided by 32 divided by 3 equals.
Equals 21.1.
So what this means, guys, is if you were to start with finish, you would produce 8.26 grams of oxygen. It would come from 21 grams or 21.1 grams of potassium chlorate.
Yeah.
You see, this is important. Why is this important, guys? Because scientists want to know how much they're going to make when they produce something. I mean, if you work at a factory where your job is to build particular chemicals, you need to be able to predict how much you're going to make from the ingredients that you have. I mean, really, bakers do this
I
all
was
the time.
going to say, I did that last night when I made cookies with my kids.
Yeah. So this method we use for chemicals, but really it can be applied at the bakery. How many cookies can you make based upon the fact that you've got 4 cups of flour or something like that? Yeah. All right.
All right, I think this is the last one.
Okay, this one's going to go to liters, so this is a little different. So we should probably go to the
Mole map.
mole map. Okay. Understands where are we going from?
This one we're going from grams to liters.
So grams of this first
of the first substance
chemical, and we
to
go up to liters.
of the second chemical.
And again, there's no line
Nope,
from here to
you must
here.
go through the land of the
So
mole.
we're going to use this fraction, and then we're going to use this fraction, and we're going to use that fraction.
Yep.
All right, so let's do that. So what we know? We know we have 12.2 grams of potassium chlorate. My question mark here is oxygen in liters. So we're going to convert from here to here. So we're going to start with our 12.2 grams of KClO3 over 1. Then we're going to say grams of KClO3 to 1 mole. This is the molar mass. And, of course, let's just add them all up, and we know now, by now that it's...
122.5.
Mr. Sims, I think you've got it memorized.
I think I'm never going to have to do that again.
Yeah. So the grams of potassium chlorate cancel. Now we need to do the...
Mole ratio.
Mole ratio, land of the mole thing, right? So we're going to say moles of KClO3 to moles of oxygen, and the ratio was 2 here and 3 there.
Okay.
Moles of KClO3 cancels, and we just have a new fraction, but it's not really new.
No, we've used it before, unit 3.
Now I've got moles of oxygen here, so I'm going to put moles of oxygen down at the bottom.
We've got to go to liters of the gas.
And this is at STP.
STP, so we use 22.4.
That's that 22.4 number Okay, numbers on top are multiplied, bottom divide, so 12.2 times 3 times 22.4 divided by 122.5 divided by 2 equals...
Equals 3.35 liters of O2.
Oxygen. So you can predict how many liters of oxygen you would produce at standard temperature and pressure. So to summarize, Mr. Sams, what do our students need to do if they're doing these problems?
You need to follow the rules that we gave you.
Rules?
Okay? Now, there are other ways to solve these, but for now, do it our way. Okay?
Yeah, because they can get more complex.
They
guys.
can get more complex, so don't try to do it in your head. Always write your units with the chemical with it.
That's right.
Always, 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 and then use that mole map. It'll be your guide. Figure out what you know and where you're headed, and just follow the lines.
And at some point, you may not need to have the mole map.
Right,
But
for now,
you
use
probably
it.
do.
Yeah.
Okay. Well, we will see you in class, or maybe we'll never see you because you're on the